All right, hello everyone. In this video, I'm going to go over some useful problems that are going to be helpful for the upcoming test. So I'll talk about vectors, there's a problem with friction, tension, and then inclined plane. So I'm just going to jump right into it, pulling some examples that I wrote down, and then also going over some of the Class K problems that we had for homework throughout the last couple weeks. So for this first one, we're going back to vectors. And all you need to do is to be able to find the magnitude and direction of a vector, right? So say we're going to be looking at a displacement vector here, and we displace 2 meters north, 12 meters west, and 12 meters or 15 meters south. So let me just write that out. So let's say I go 2 meters north. So I'm going to go 2 meters north. And let me see what else. Yeah, 12 meters west and 15 meters south. So it's not to scale, but close enough. So I got 12 meters west. And then I'm going to go 15 meters south. Okay, so graphically, I want to explain what I'm doing graphically, and then I'm going to show you the analytical solution. So the way you add vectors is you use what's called the tip-to-tail method, right? So I have these three vectors here, and whatever vector I'm adding, say I choose a 2 meter north displacement vector, what I do is from the tip of the first vector, that's where I place the tail of the next vector. Okay, so that's why it's called the tip-to-tail method. Something that's interesting about the tip-to-tail method is that it doesn't matter what order you do it in. Okay, so you can add the vectors in any order. It's a commutative property, just like with normal addition. 2 plus 7 is the same thing as 7 plus 2, right? So you can do the same thing with vectors. And when you line up all your vectors using the tip-to-tail method, to get the resultant vector, you basically go from your starting point to your ending point, right? So this is where I end, this is where I started. I'm going to draw a vector like this, and that's my resultant. And it's going to be pointing in a certain direction, and it's going to have a certain size, right? So to demonstrate the tip-to-tail method and the commutative property of vectors, I'm going to add them in the opposite order, right? So let's say I started with, instead of the 2 meters north, I started with the 15 meters going south, right? So if I start with the 15 meters going south, and this is not going to be perfectly to scale, but I'm just going to get it close enough. I just want to kind of show the idea. All right, so this is my 15 meters south, 12 meters west, and I go 2 meters north. I'm going to end up with the same vector, right? So I started here, I ended over here, and I just draw a vector, and then again, that's my resultant. Okay, so that's a kind of like visual graphical understanding of how you add vectors. Now let's do it analytically. So what you need to do is you have to actually just find the sum of the x and y components, right? So let's say, okay, you have to sum the x components and sum the y components. And then if you want to find your resultant vector, you have this formula here, right? So it's just Pythagorean theorem. So you just do the Pythagorean theorem. I don't know why it's doing that. All right, stop. Okay, y squared. Okay, so you just take the square root of the sum of the squares of the components, and then to find a direction, you're going to have to do the inverse tan of y over x. To kind of see where that comes from, I'm just going to draw a right triangle, right? So say I have an x component here, a sum of the y components here. I'm basically creating a right triangle, and the relationship between those components, right, is the resultant, right? So this would be r, and we can clearly see that's just a right triangle. And if you do the math, you want to solve for theta, the direction is pointing in, you do inverse tan. Now there's some special rules depending on what quadrant you're in, and I'll get to it with this problem. First, I want to solve it, and I want to show you how to apply the special rules. So here, let's just find the sum of the components. So the sum of the x components, I'm going to do that first. All I have is the 12 meters west, right? So the 12 meters west, I'm going to consider going to the left to be negative, right? So if I look at my coordinate system, right, I'm going to measure all my angles with respect to the positive x-axis, okay? And this would be east, this is north, west, and south, okay? So here, 12 meters west, I know I'm going in a negative x direction, so I'm just going to say it's negative 12 meters. And that's all I have in the x direction. Now for my y components, I have 2 meters north and 15 meters south, right? So I have 2 meters north, that's positive 2. And I'm going to add my negative 15 meters, right? That's my south, that's my 15 meters south. So here I have negative 13. And these are my components here. So my y component is negative 13, my x component is negative 12, and now I just have to add them up using the formula. So r is equal to the square root of negative 12 quantity squared plus negative 15 quantity squared. And, oh, whoops, I put negative 15, it's negative 13 because I had to add the 2 meters north, so negative 13 quantity squared. Now for this, well, we're going to bust out our calculator. Let's see here. So we got 12 squared is 144 plus 13 squared, that's 169. Add them up, 313. So this is the square root of 313. And on our calculator, it says 17.7. So it's about 17.7 approximately. So that's my resultant. Now I need to specify the direction. So the rules, depending on what quadrant you're in, you just have to think about what the coordinates are. So my sum of my x and y components are both negative. That means I'm in quadrant 3, right? So if I have a negative x and a negative y, if you think about your coordinate system, you're in quadrant 3, all right? And then quadrant 2 would be negative x, positive y. And then quadrant 1 would be obviously positive x. I'll put a little positive sign. So positive x, positive y. And then quadrant 4 would be, actually positive x and negative y, okay? The rules for the quadrants is if you're in quadrant 1, you do nothing for the angle, right? So I'm actually going to write it out like this. So I'm going to do, so your direction is just going to be inverse tan of y over x, okay? For quadrant 2 and for quadrant 3, so 2 and 3, right? You still do the same thing, inverse tan of y over x, but you're going to end up with a negative number, right? Because if you do positive y divided by negative x, or if you do, well, that's for quadrant 2, you're going to have positive y divided by negative x, and then quadrant 3, you have negative y over negative x. It's going to be, you're going to get a positive ratio for that one. Actually, let me just do them separate just to make it clear. So I don't want anyone to get confused about the signs. So in quadrant 2, because you're doing the inverse tan of a positive y, right? So we have positive y over negative x, right? You're going to end up with a negative angle. And all you have to do is add 180 degrees to that. And that's going to give you the direction, right? So it should be some angle between 90 and 180, right? So if I add some negative angle to 180 degrees, I'm going to end up with an angle between 90 and 180, right? Because this inverse tan of positive y over negative x is going to give me some number between 0 and 90, but it's going to be negative for the theta. So that's the rule for quadrant 2. For quadrant 3, you're again going to do inverse tan, except now you have negative y and negative x, right? So quadrant 3 is going to look a lot like quadrant 1, except you just have to add 180 to it. All right, and it's going to give you an angle between 180 and 270. All right, so then quadrant 4, finally, you have inverse tan of a negative y and a positive x. And then for this one, you have to add 360. Okay? So let's figure out our direction. We know we're in quadrant 3 because it's going down and to the left. So my direction of this vector has to be between 180 and 270. That's how you want to think about it. Okay, so let me just do that here. So I'm going to do inverse tan of y over x. That being the inverse tan, I'm just going to write in what the values are. So I should have a negative y and a negative x because I'm in quadrant 3, which I do. My y component is negative 13. My x component is negative 12. And with that, I have, again, use your calculator. So inverse tan negative 13 over negative 12. I get 47.3 degrees. So 47.3 degrees, but I have to add 180 to it, right? Because obviously 47.3 degrees, that'd be in quadrant 1, and we're in quadrant 3, right? So I add 180 to that. I'll just do it on my calculator so I don't mess up. 227.3. Okay, so 227.3 degrees. And if we're dealing with 3 sig figs, right, let's just say we have 3 sig figs, I'll just write out 227. Okay, now my vector, my displacement vector, or I'm just going to write out my resultant displacement because I displaced 3 times. I moved up 2 meters north, to the left 12 meters west, and down 15 meters south, right? So my resultant displacement is going to be 17.7 meters at 227 degrees. And that's it. All right. One last thing, if you needed to find the x and y component, say I gave you a resultant vector with a specified direction, right? And you need to find the x and y components. Remember that if your theta is, if your direction is specified with a positive x-axis, you do this. So you have r cosine theta for the x component and r sine theta for the y component. And then that's pretty much a brief overview of vectors. I'm confident we'll do well on this part because on the vector quiz we did fairly well. Now let's look at some tension problems and then a friction problem. So the other 3 examples I want to go over, some tension, friction, and the inclined plane. And what I'm going to do is there are some useful problems from the class kick that we'll go over. And we've seen these before. I helped anyone who had any questions, I helped out, but I want to make sure we really know how to do these problems. So I'm just going to do the problems as a student preview, and these are going to be useful kind of problems for the test, right? I want to make sure that we know how to approach them. So this problem, this is from day 6, page 4. We have a sign that has a weight of 750 newtons. Cable A is attached in this manner, and the angle is 30 degrees with respect to the wall. And then cable B is horizontal. So we got to figure out what the tension in cable B is. Now, with every force problem, you want to just start with a free body diagram. Okay, so here I'm just going to draw out the situation. I have TA, that's my tension in cable A. I know that this angle theta here is 30 degrees. So there's this angle with respect to the wall that's 30 degrees. And then cable A is attached to this point, which is hanging onto the sign, right? I'm just going to draw as a box. And we know that the sign has a weight of 750 newtons. And then there's a tension in cable B. I'm going to label it TB. And that's also connected to a wall, right? So I'm going to draw my... actually, I'll just leave it as is. Let's see here. So just know these are attached to a wall. The cables aren't moving. The box is not moving. We're in equilibrium. Right, so because the system's at rest and staying at rest, we know that the net force is 0 and that the force is balanced, right? So whatever pulls to the left has to equal what pulls to the right, and whatever's pulling up has to equal what's pulling down. If that were not the case, this system would accelerate, right? And obviously it's not. The sign is just hanging off of the cables, and we're in equilibrium. So we know for a fact that the forces have to balance. So that's how you want to reason about these problems. You draw your free body diagram. You think about what's going on in the problem, and then you have to formulate your expressions, right? So how do these forces relate to each other using Newton's laws? So what I'm going to do is I'm going to look at I'm going to make an equation for the horizontal forces, right? So whatever's pulling to the left has to equal what's pulling to the right, and I know that since we're in equilibrium, right? So if I think about the forces that's pulling to the left, well, it's a component of TA. Right? So I'm analyzing the forces at this point here, where it's holding up the sign. TB is pulling to the right, a component of TA is pulling to the left, and then the question is which component. So this is the part that a lot of students were confused on, because it's like, wait, isn't the x component always cosine? Well, it depends. In this particular example, you just want to draw out the right triangle, and we see that this component here, that component right over there, is pulling to the left, but it's opposite of the 30-degree angle, right? So this is why you want to remember SOHCAHTOA, right? So if I just write out SOHCAHTOA so we can remember the ratios in terms of what trig function we want to use, I know that this side here, that's the opposite side. And the actual value for the tension in cable A, that's the hypotenuse. So I have to actually use sine. Okay, because that's the opposite side. The hypotenuse is TA, right? So if I do the math, I see that this component here is TA times the sine of 30. All right, so I have T sub A times the sine of 30. That's the component of the tension that's pulling to the left. And I know that has to equal the tension in cable B. Cable B is just pulling to the right at this point, where the sine's being held, that little hook over there, where the cable's attached to the sine. TB is pulling it to the right. The component of TA that's pulling it to the left is TA sine 30. All right. Now in the y direction, what's the component of TA that's holding up the box? Well, it turns out to be the cosine. So that little component over here, that's TA cosine 30. All right. So TA times the cosine, cosine 30, that has to equal the weight of the sine, right, which is 750 newtons. I'll put this in parentheses so you don't confuse the unit of newtons with a variable. So I have these expressions, and basically I have to solve for TB, right? So in order to solve for TB, I need TA, right, which I don't have. But to solve for TA, I can just use the second equation, right? So let's do that first. Let's solve for TA, and then using the value for TA, we can solve for TB, all right? So I'm going to solve for TA first. In order to solve for TA, I'm going to need to divide both sides by the cosine of 30, right? So TA is equal to 750 newtons, right, divided by the cosine of 30. And you're going to need to bust out the calculator for this one. Let's see here. So 750 divided by the cosine of 30, I got 866. Whoops, here, 866 newtons. Okay, so that's the first part. I now know TA. I can solve for TB because according to my first equation, TB is equal to TA times the sine of 30. So I just took 866 newtons, that's TA, multiplied by the sine of 30, and just plug it into my calculator. I already know the sine of 30 is 1/2, so this just comes out to 433. But always just use your calculator if you're unsure. And that's my answer. That's what TB is. So let's check. Let's make sure we got this right. And yeah. Oh, they actually got a slightly different value. That's interesting. It must be due to rounding, but I got 433 because we got 866 for the tension in cable A. So yeah, 433. That's what we got from our calculations. And yeah, that's pretty much all there is to that. Here, let me make sure I didn't type anything wrong. So I'm gonna look at my calculator. So no, it looks good. So I did 750 divided by cosine 30, and then I multiplied that by sine 30, and I got 433. Alrighty, so at this point, let's look at the next problem. Wait, actually, there's another one I wanted to go over. Oh, right, this one. So I want to go over page 3 as well. So we just did page 4. That was a good example of a tension problem. Let's do page 3, which is more about vectors, right? So this is more about using vectors to figure out a problem about forces. So we have 5 forces here that act on an object, 60 newtons at 90 degrees, 40 newtons at 0 degrees, 80 newtons at 270, 40. Okay, so you got all these different forces. And we need to find the magnitude and direction of the 6th force that would produce equilibrium. Okay, so we need to figure out how to produce equilibrium. So we know for equilibrium, F net has to equal 0, which means that the forces balance. All right, so the way that we want to approach this particular problem is that we look at the forces in the x direction and we look at the forces in the y direction, and we need to figure out what force is going to bring those to zero, right? So we need to figure out, I'm writing it out just so we understand the flow of the problem, to figure out the forces in x direction and in y direction. All right, so we need to figure out what they are, and then what needs to be added to have a result of 0. Right, we need our net force to be 0. That's what it means to be in equilibrium. So what I'm going to do is I'm going to solve for the x and y components for each of these vectors, and then just add them up. So, right, what's the sum of the x components? What's the sum of the y components? And then how do I get that to 0? So here we have 60 newtons at 90 degrees. All right, and for this is when you're going to use your formulas here. So cosine theta and y is equal to r sine theta. Keep in mind, this works when you specify the direction with respect to the positive x-axis. So if we say the positive x-axis is 0 degrees, all right, positive y-axis is 90 degrees, this is 180, this is 270, right, and then we go full circle back to 0. So if I specify my direction using this coordinate system, then I can use these formulas, right? In the previous problem, it didn't work that way because that's not the angle that I specified. Right, I have some angle here with respect to the vertical. That's 30 degrees. I draw out my triangle to make sure I don't mess up what the component has to be. All right. So these are, two separate situations you have to keep in mind. But if you're just given vectors at a particular direction, you can just use these equations. So let's get started. I'm just going to look at the x and y components for all the vectors. So the first vector, I have 60 newtons at 90 degrees. So 60 newtons at 90 degrees. Now, personally, you could do the sine and cosine for each and every single one of these vectors, but that's going to take quite a while. You don't actually have to do that if you think about what's going on. So, for example, this first one, 60 newtons at 90 degrees, I know that's just going straight up, right? So if I did 60 cosine 90, I'm going to get 0. If I did 60 sine 90, I'm going to get positive 60, right? But you can also reason that just by thinking about what the coordinate system is. So this is actually going to save you quite a bit of time. That's how I'm going to approach this problem. But if you want to do it in a very formulaic way, you could actually just do the sine and cosine for each and every one of these vectors, right? And then just add up all the x components and add up all the y components. But me personally, I already know that this here, this vector is going to be 60 newtons going up, right? So this is in the positive y direction. This is going in the positive y direction. Here, the 40 newtons is going to the right. The 80 newtons is going to the left. The 40 newtons is going, the 80 newtons here is going down because it's at 270. The 40 newtons is going to the left. And then only the last vector do we have to actually look at the x and y components. So the vector 5, that's going to be the one that has a horizontal and a vertical component. I think the best way to organize this problem is I'm just going to write it out on like a table and do like a running total. Right, so here I have vector 1. I'm going to look at the sum of the x and y components. This is just to organize our work. So for vector 1, the x component is, 0, right? If you do 60 cosine 90, you get 0. And the y component is positive 60, right? So I'm going to put a little plus sign to signal that it's positive, it's going up. For the second vector, it's going at 40 newtons at 0 degrees. Okay, I know it's going to the right, positive x direction. So this is, if I did 40 cosine 0, I would just end up with positive 40. And my y component would be 0. For the third vector, this was going straight down. Okay, again, you can use the trig functions if you want, and you're still going to get the same answers. But if you reason, you'll be able to do this more quickly. So 80 if you did 80 cosine of 270, you'd get 0. But I already know it has to be 0. It's going straight down. And then if you did 80 sine 270, you would get negative 80, right? Because, again, it's going straight down. So that's considered negative y. For vector number 4, I have 40 newtons at 180. I know it's going to the left, so it's going to be negative 40. And the sine is going to end up being 0. There's no component in the y direction. And then finally, for the 5th vector, now this is when we have to actually bust out the calculator because it's at 60 degrees. And one of those components is not going to be simple. Well, actually, the x component is easy because cosine 60 is just 1/2. But just use your calculator. When you have an angle like this, just plug it into the calculator so you don't mess up. So 50 cosine 60, right, just as I said, it's positive 25. Okay, and now I got to do 50 times sine 60. So 50 times the sine of 60. And I get 43.3. So positive 43.3. All right, now let's add them up. So from x components, I have 40 minus 40 plus 25. Okay, I just end up with positive 25. And then here I got plus 60 minus 80. That's negative 20 plus 43.3. That's positive 23.3. And again, you don't have to put a positive sign. I'm just doing that to signal what's positive, what's negative. So yeah, those are my x and y components. Now, here's where it's easy to mess up, because we get used to the idea of like, okay, that's my sum of the x and y components. Now I just need to find the resultant vector. That's actually not what this problem's asking about. If the problem were to say, all right, these are your 5 force vector, what's the net force? Okay, and then you can do that. That's going to be the resultant of these 5 forces. But that's not what it's asking. It's asking, what are the magnitude and direction of the 6th force that would produce equilibrium, right? So it's like, what force do I need to apply in order to cancel everything out, basically? Okay, so what I'm going to do is I need to apply the opposite, right? So because I need the net force in the x and y directions to add to 0, the total components to be 0, well, my 6th force has x component of negative 25 newtons. And it has a y component of negative 23.3 newtons. All right. So that's what the problem's asking for. Is like, okay, what is that 6th force to bring it into equilibrium? Because if I add this 6th force to my the first 5 forces that I have, right? Obviously, positive 25 plus negative 25, that's 0. And then positive 23.3 plus negative 23.3, again, that comes out to 0. And that's what we're trying to do here. We're trying to produce equilibrium where the net force is 0. So now all I need to do is find the magnitude and direction of the 6th force. So I'm going to use the equations, square root of x squared plus y squared for the resultant. Let's just plug in the numbers. All right, so negative 25 quantity squared plus negative 23.3 quantity squared. Okay. And if I do that, this one you definitely want to use a calculator. So 25 squared, that's 625. And then I'm going to add that to 23.3 squared. Okay. I come out with square root of 1167.89. Okay. All right, so I'm going to do that all in one step. So I'm going to take the square root of that. And I end up with 34.17. So here I got 3 sig figs, so I'm going to write it out as 34.2. Newtons, right? This is a force vector. So 34.2 newtons, that's my resultant. And then I need to do the inverse tan of y over x. So here I have a y component of negative 23.3 and an x component of negative 25. Since both my components are negative, I know that I'm in the 3rd quadrant, right? I'm in quadrant 3. So I'm going to need to add 180 to that. All right, so let's just do the math. If I do inverse tan 23.3 over 25, let's see, delete, okay. I get 42.98. That's basically 43, right? And if I add 180 to it, yeah, so that's 222. Or I'm sorry, 222.98, which is basically 223. And did I get this right? So 34.2 newtons at 223 degrees. That's the direction of the 6th force that I have to add. And you check and see, yeah, there we go. 34.2 at 223. Alrighty. So that's how you do those problems. Those are from day 6, and those will be helpful for the exam because we have a problem dealing with tensions at an angle, and we have a problem with equilibrium. Using vectors, that is. So one more problem, actually 2 more, right? So one I'm going to write out on the notes, but I want to go over, this was another problem. I believe it was day 11. All right, so let me check. I have it here. Yeah, day 11, page 4. That's the one I wanted to look at. So here, let me do student preview. If it wants to load sometime today. Oh, wait, I know what's going on. Okay. There we go. Okay. So let's do, which one was it? Page 4. Yes, the refrigerator problem. All right, so this one was another one that a lot of students had questions on. And yeah, we need to know how to do it. So here the refrigerator is stopped working, and Mr. Rich is responsible for pushing it up a 12-degree incline by the gym. He pushes it the 130 kilogram refrigerator with a force of 475, and mu sub k is 1.05 between the floor and the refrigerator. What is the resulting acceleration of the refrigerator? All right, so given that there's an acceleration, well, we have to analyze the forces and see if they're unbalanced. And if they are, then the net force is equal to mass times acceleration. And that's how we're going to approach this problem, right? So we need to find out what that net force is divided by the mass, and that's how we get the acceleration of the system. But the harder part is actually, well, doing the work, right? So here I'm going to draw out the free body diagram. I know that I have a force of gravity going straight down. This angle here, theta, this is supposed to be 12 degrees. Okay. And I know I have a normal force that is perpendicular to the plane. I'm going to write it out, force normal. I have a friction force, right? Because there's a mu sub k. It says it in the problem. So there's a coefficient of kinetic friction of 0.105. Now, something that's very important is understanding which direction that friction has to go. Okay, so it says here he's pushing it up the 12-degree incline. All right, he's pushing it up the plane. So I'm moving up the plane. That's my direction of my velocity. Friction opposes motion. All right, so that's something that's very important to note. If this object is sliding up the inclined plane, the friction force will be pointing down the inclined plane. It's going to be going this way. This is going to be the direction of my friction force. Right, that's the direction of my friction force. Right, this is just gravity. So my force of gravity is there. This is something that's very, very important because you have to remember how friction works. It opposes motion, because we're going to see in the later parts that when the refrigerator is going down the inclined plane, friction is going to actually be going in the opposite direction. It's going to be going up the plane. And that just has to do with how friction fundamentally works. You look at how these surfaces are sliding past each other. In this case, the refrigerator is sliding up the inclined plane, up and to the right, and the floor is sliding past it, it's going down to the left. The friction force being applied is going to be going down to the left. All right. So now you just have to actually, so we have the free body diagram. That's always the first step. You draw it out, you reason through it, and then you actually start setting up your equations. The trick to the inclined plane, as we've discussed many times, is we're going to actually find the components of gravity. Right. That's how you're going to approach it. Okay, and this has to go with the general idea to make these problems easier to solve. There's this heuristic, there's this way to approach it where you call the direction of acceleration positive, right? You think about how the system's accelerating, you consider that to be positive. That's the positive direction, and if we do that, right, it's as if we are kind of rotating our coordinate system a little bit by 12 degrees. And that means we're going to have to find the components of gravity. So that's the trick to approaching the inclined plane. If you don't do that, it's going to be a headache. and you're going to have a net force in the x and y directions. We don't want that. We want our net force to be going in a particular direction. In this case, it's going to be positive x direction. There's not going to be a net force in the y direction. This thing's not on an elevator or, falling out of the sky. The only acceleration is going up the inclined plane, so that's the direction we're going to look at. Now, the thing that's important, I'm actually going to put this in the notes, all right, because I want to really, really emphasize it. So it's a little bit more clear. The class kick, the level of detail is a little rough. So when you are drawing your gravity force vector, this is very, very, very important for the inclined plane. All right, I just want to emphasize this. If this is the angle of your plane, theta, okay, your components for gravity, right? So this is a component that is perpendicular to the plane, and that's the component that's parallel to the plane. Actually, let me even use different colors. I want to make this as clear as I can possibly make it. I'm going to use blue for the component that is parallel to the plane. Okay, so this angle here, this theta, is equal to the angle of the inclined plane, right? And if you think about it, basically what's happening is as the plane is getting steeper and steeper, okay, the force of gravity is going to deviate by the same amount. All right, so if this plane was horizontal, right, then, well, this theta, this interior angle, would be 0, right? And then you just have the force of gravity equaling normal force. For the inclined plane, right, as you increase the degree of the incline, right, the vertical component of gravity, the one that's perpendicular to the plane, that's going to get smaller, and the horizontal component of gravity is going to get bigger. All right, that's going to have it slide down the plane. So here, it's important to remember SOHCAHTOA, right, because this is a very common mistake. In this case, the component that is perpendicular to the plane, we're so used to the y components being cosine, but you have to draw it out. This is why it's so important to draw it out. We see here, because of the way the angle is measured with respect to the force of gravity, this is actually the opposite side. I'm sorry. The yellow is the adjacent side. So the yellow is the adjacent side. That's going to be cosine. So that component that is perpendicular to the plane. I'm always used to doing the parallel one first. But this yellow one, the one that's perpendicular to the plane, that's going to be cosine. And the one that's parallel to the plane, this one right here, what we can think of as our x component, that's going to be mg sine theta. And just to be as thorough as possible, where does the mg come from? Well, we know that the force of gravity, that's just the weight force. That's equal to mass times the gravitational acceleration, which is 9.8 meters per second squared on Earth. Okay, so I just wanted to clarify this point, right? Because I know we've gone over it many times, but it doesn't hurt to go over it again to make sure we don't mess this up. So this is how you decompose the components for gravity, right, when we're dealing with the inclined plane. That's how you want to approach the problem. So let's go back to the classic example. And as we stated here, we know that this component, that component there is the mg sine theta, and then this component over here that's perpendicular to the plane is the mg cosine theta. So now let's look at our forces. So I'm calling positive x direction going up the inclined plane. And we got to see what forces are acting in the x direction. Well, we have friction force that's going in the negative x direction, right? It's going down the inclined plane. And mg sine theta is doing the same thing. It's also going down the inclined plane. So here, I forgot one more force on the free body diagram, right? So we're not done yet. We have to do the applied force of 475, right? Because obviously if that wasn't there, this thing would just slide down. It's not doing that. It's accelerating up the plane. So we know we have a 475 Newton force that's being applied. So I'm going to use Newton's second law. I know F net equals ma. This box is, this refrigerator is going to be accelerating up the inclined plane. In terms of what's positive and what's negative, well, I look at how I set up my free body diagram. I see the 475 is going in the positive x direction. So that's positive. So I have my 475 newtons of applied force. And then I have mg sine theta that's going down the plane, and my force of friction. Right, so that's how I set up my equation for the x direction. Now in the y direction, I have normal force going up, I should also specify that in the y direction, the net force is actually 0. So this refrigerator is accelerating up the inclined plane, right? It's not accelerating, based on how my coordinate system is set up. It's not like this inclined plane is going up or down in an elevator or accelerating in the y direction. It's just accelerating going up the inclined plane. So I know my net force here is going to be 0. So the force is balanced in the y direction. All right, I just want to specify that. So I know that I have normal force going up. I got mg sine theta going down. All right, and that's what I'm going to write out. So normal force is going up. Mg sine theta is going down. Oh, whoops. What am I saying? Mg sine theta is... Good thing I catch that. It's cosine theta. See, this is the issue. It's not as clear on Classkick, or I need to zoom in. Hold on. I can zoom in a little bit, right? There we go. All right, there we go. Let's make it easier to read. So this is cosine theta. And actually, that's very annoying to do on the iPad, unfortunately. So I'm going to zoom out a little bit so I can actually touch the side without writing on the page. Okay, a little bit better. So yeah, normal force is equal to mg times the cosine of theta. And we have everything we need to start approaching this problem. So we have m. We know it's 130 kilograms, right? So m is 130 kilograms. We know g is 9.8 meters per second squared. We don't have friction. We don't have the acceleration. But we can figure out friction from the normal force. All right, so that's what you have to do. So the force of friction is equal to the coefficient of friction times the normal force. All right, and we know the normal force has to equal mg cosine theta. All right, so here I have mu times mg cosine theta. I'm going to put this in parentheses so it's clear, like, hey, I'm just substituting from my equations in the y direction. I know normal force is mg cosine theta. I'm just going to plug it in right there. So now I am going to plug this back into the first equation, right? So this mg cosine theta, I'm going to put it here for friction. And I'm going to rewrite this. So I'm going to highlight this, draw little arrows to show that we're working on this equation. So I have ma is equal to the 475 minus mg sine theta minus mu times mg cosine theta. All right, so at this point, we can just start plugging in numbers and solving for the acceleration. Personally, I would do it in variables, but I think I've noticed it's a lot easier for students to just plug in the numbers. If we're given values here, we can just plug in the values. So let's do it. I'm going to plug in all the known values and then solve for the unknown. So the mass here, we know it's 130. So we have 130 kilograms times the acceleration equals 475 newtons minus mg sine theta, right? So m is 130. So 130 kilograms times 9.8 meters per second squared times the sine of 12 degrees minus mu, which is 0.105, times 130 times 9.8. I just realized that I probably shouldn't have necessarily put units, but you don't have to put units when you're calculating. I'm just trying to make it as easy to see as possible, but I guess it's not so easy. All right, there's a lot of calculations here. So this is what we end up with. You can just plug all this into your calculator, the 475 minus 130 times 9.8 times sine of 12, and then you have the 0.105 times 130 times 9.8 times cosine of 12 degrees. All right, so let's get through all that. I will put this in my calculator. All right, so here, the 130, I'll do that part first. So 130 times 9.8 times the sine of 12. I got here 264.9. Let's see here. So I'll write the final answer with the proper number of sig figs. But for the calculations, I'm just going to write it out like this. So 264. All right. So this part here, this is 264.9. 264.9 newtons. And then this part over here, this is going to be, again, 130 times 9.8 times 0.105 times the cosine of 12. And I get 130.8, roughly. Okay, that's minus. And then this is the 475 newtons minus that. So 475 minus 264.9 minus 130.8. I'm going to do all that now. So 475 minus 264.9 minus 130.8. And I end up with 79.3. So 79.3 newtons. That's equal to my net force, which is 130 kilograms times the acceleration. And then we can finally solve for the acceleration by dividing both sides by 130. I'm going to do that now. And I get 0.61 meters per second squared. That's my final answer. Let's see if we got it. Hey, there we go. 0.61 meters per second squared. So as you can see, this problem, it takes a little while. And that's just how it is. You know, just making sure that you set up your free body diagram appropriately. You go through the equations. We related the x and y directions using the friction equation. So, right, so this part's key here. So knowing the equation for friction, mu times normal force. And that's, you just basically calculate from there. If you have extra time at the end of the test, you're definitely going to want to double check your calculations. Because as you can see, you mess up one little thing, unfortunately, you end up with the incorrect value. But also, that being said, there is partial credit. I will run through all the calculations I see on the paper. If you mess up one little thing, it's not like you get the entire problem wrong. That'd be ridiculous. But you have to, double check, take it slow, don't rush, right? We have the entire class period to work on the test. All right, so now going through this part, how much would Mr. Rich have to push in terms of newtons to push the elevator with a constant velocity? Okay, so this one is, we have the exact same setup. I'm not going to run through it again, all right, because there's nothing else that's changed. The mass is the same. The coefficient of friction is the same. The only thing that's different is changing that 475. So what do I have to make the 475 in order to have this refrigerator be pushed up with a constant velocity? Well, notice I ended up with a net force of 79.3. Right, so from previous problem, my net force ended up being 79.3. Okay, so I just need to push with a force that is less than the 475, right? So my original force, so the original force applied was equal to 475 newtons. Okay, and I ended up with a net force of 479.3. So what I'm going to do is I'm just going to push a little bit less, right? So I'm not going to push as hard. I pushed with 475, and it was going up the inclined plane, or at least Mr. Rich was pushing with 475. So if he pushes with 79.3 newtons less than the 475, it should end up with a net force of 0. That's what it means to have constant velocity. Constant velocity means that the net force is 0. Right, so what do I need to push with so that the net force is 0? Well, I'm just going to take 475 minus 79.3. Right, that's the reasoning for this problem. Minus 79.3. and I end up with 395.7. Right? That's going to be my new applied force, basically. So just to reiterate, I hope this makes sense. So in the original problem, the elevator was, or the refrigerator, I'm sorry, was accelerating up with 0.61 meters per second squared. And that's because Mr. Rich was pushing with 475 newtons of force. In this problem here, it's saying how hard would he have to push so it moves up with constant velocity. So in that case, you actually want to push it less hard, right? Because we ended up with a positive net force. We want our net force to be 0 if we want to push with constant velocity. So all I do is I take 475 minus 79.3 so that my net force ends up being 0, right? Basically, if I add up the mg sine theta and the mu mg cosine theta from the previous problem, I should end up with about 395.7, and that's how hard I'm going to push so that the net force is 0. So let's check our answer. If we do 3 sig figs, yeah, we get 396. Yeah, so that's the right answer. So our final answer with 3 sig figs, 396 newtons. Actually, I'll write it over here. 396 newtons, that's our formal answer. And then over here, our formal answer is 0.61 meters per second squared. Okay. Now, finally, the last part of this problem. Still not done, but we're about to be done. All of a sudden, Mr. Rich slips, and the refrigerator starts to slide down the ramp. How much force does he have to apply to keep it sliding down at a constant velocity? So believe it or not, this problem is actually different. All right, and I want to explain why using a free body diagram. This goes back to what I was talking about before. The direction of friction. So now the inclined plane, now it's moving down the incline, and friction opposes motion. Friction opposes motion, right? So if this refrigerator is sliding down, right, the surface of the refrigerator touching the surface of the plane, if the refrigerator is sliding down the inclined plane down to the left, friction is going the other way. So right off the bat, I'm going to draw a force vector here that is friction. This is my friction force vector. In the original problem, friction was going down and to the left, right, going down the inclined plane. In this problem here, it's going up the inclined plane, and that's because the refrigerator is sliding down, right? So that was the key part. That's what tripped people up with this problem in terms of how to solve it, is understanding now we're dealing with a new free body diagram because the situation has changed. So I'm going to draw it out again just to be thorough. So here we got force of gravity. Here we have our components here. All right, these are our components. We have normal force going up the inclined plane, or perpendicular to the plane. And now here we have to see how hard does he have to push it in order to keep it going down at a constant velocity. So what I'm going to do to make this problem a little bit more straightforward to solve, I'm going to look back at my numerical calculations here. So I calculated that the mg sine 12 was 264.9. And I calculated that the friction was 130.8. All right, just ignore the positive and negatives for now. We're just looking at the magnitudes. So I know that the mg sine theta, the part that's pulling it down the plane in this problem, right, that's the mg sine theta, that's actually bigger, larger in magnitude than the friction force. All right, so in order to keep this going at constant velocity, again, this is going at constant velocity, I need a net force equal to 0. Right, I know this friction force has a magnitude. I'm just going to write it on the free body diagram. It makes our lives a lot easier. So 130.8, that's the magnitude of this friction force, 130.8. And the magnitude of this mg sine theta, right, so I'm just going to draw this here. That's the mg sine theta, that component there. We know that has to equal 26.49. I'm sorry, what am I saying? 26, 264.9. Yes, 264 newtons. Okay, so these are our values, and we need to see what force needs to be applied in order to keep it going up the inclined plane, right? So what force does Mr. Rich, he just slipped, now the refrigerator is sliding down. What force does he need to apply in order to keep it at a constant velocity, right? So I'm just going to look at my forces in the x direction. I don't have to do the analysis for the y direction, right? Because I already did it here. All the analysis is already essentially done over here. We're just switching one little situation in these other two examples. So in this one, we know now friction is going up the inclined plane. How much force does he have to apply? Well, I'm going to consider going up the inclined plane. Actually, here, 1 second. I want to clarify something. So this object's not going to be accelerating, right? So it doesn't actually matter what direction we call positive or negative. We just know that the forces balance, right? So the forces have to balance out. So the forces that are going up and to the right, so they're going up the plane, that's force of friction and force applied. The force that's going down the plane is the parallel component of gravity, this mg sine theta. So mg sine theta, that's what's sliding, that's what's pulling the refrigerator down the plane. Friction's actually going against it, right? It's opposing the motion, and Mr. Rich is going to be pushing it, right? So those two forces are going up the plane. So I set that equal, so force of friction plus the force applied. We already know what these two values are from the previous problem, right? 264.9 and 130.8. So I'm just going to write those values in. So 264.9, that's my mg sine theta. My force of friction, we calculated to be 130.8. And then I have my force applied, right? So then you just have to take the difference of these two numbers. And I'm going to do that now. So 264.9 minus 130.8. Whoops. Let's see. I got 134.1. So I ended up with a force applied of 134.1 using 3 sig figs, 134. Let's see if we got that right. Hey, there we go. Okay. So recap. This is a long problem. We had to do the analysis for the first part to write out our free body diagram, write out our equations, and perform the bulk of the calculations. Okay. As a side note, I put the numbers down on each part of the calculation to make my life easier, but also it helped out because I didn't have to redo the analysis on the other parts. That is true for this particular problem because nothing else changed. If I gave you a different problem with a different, say it's not Mr. Rich, it's some other guy, and it's not a refrigerator, it's a washing machine with a different mass and, you know, a different coefficient of friction because different plane, well, you got to do it all over again. All right, it's only for this particular problem where it just kept following up where we can reuse the same values, right? So that actually saved us some time. I knew that the mg sine theta and the mu mg cosine theta, those values weren't going to change because they didn't change those in these situations. The only thing that was changing for all three of these problems was the force that Mr. Rich was applying. In the first case, he's applying a 475 Newton force, so the refrigerator accelerates up the plane. In the second case, he pushes it a little bit less. He pushes it a little bit less so it no longer accelerates. And then we had to figure out what that force value was, the 396. And then in the final case, the thing that tripped most people up, what I noticed when I was helping out students with this problem, is the direction of friction. The fact that the refrigerator is now sliding down the inclined plane, the friction force is going to be going up the inclined plane. And that is because friction opposes motion. But again, we reuse the same numbers that we already calculated, and we know that the force applied is 134 newtons. And that's pretty much it for inclined plane. One last problem I want to do, because I know this video has been going on for a little while, but we need to know how to do it. So we did vectors, we did inclined plane, we did some tension. Okay, so let's do this problem. All right, so there's an example with friction where there's an applied force at an angle, right? So this is not as bad as inclined plane in my opinion, but again, you still need to set up your free body diagrams. It's just the same process as always. You draw your free body diagram, you write out your equations for the forces, and then you have to, figure out your unknowns. So for this one, I'm kind of making up some numbers, but I want to make sure we know how to approach it. So let's say the weight is 120, mu sub k is 0.5, 30 degrees below the horizontal. All right, so that's the part I really wanted to emphasize. So here, I'm just going to draw it out again. So let's say we have a box here. All right, and there's some friction, and we're going to say that the friction is 0.5. All right, this box is going to travel 2 meters, and we need to figure out how long it takes to travel 2 meters. Some details that you have. Let me draw my forces in a different color here. So I know that I have an applied force, right? So let's draw a free body diagram. So we know that this is going to have a normal force between the box and the ground. There's going to be a weight force. That's the force of gravity. I'm making my normal force a little bit larger than the gravity force. You're going to see why in a second. So there's a force being applied at an angle. Okay, it's being applied at an angle, all right? And that's the little trick to approaching this problem. Because the force is being applied at an angle, we have to look at the horizontal and vertical components. Now, on a free body diagram, you don't have to draw the dotted lines. You're supposed to just draw the actual forces. But in terms of the analysis, it's a little bit easier to visualize what's going on. So I see this applied force. What do we make it? I just made it some number that kind of makes sense. What did I decide on? And actually, let me think about this for a second, because I want to make a number that makes sense. Let me see here. I'm going to do a quick math real quick because I don't want to mess this up. Yeah, that works. Okay, let's say it's 200. 200 newtons. All right, that's the number I'm gonna pick. So this applied force is 200 newtons. So this is my force applied. Force applied. I'm going to say it's 200 newtons. And it's at 30 degrees below the horizontal. Okay, so it's going down and to the right. So this angle theta here, this angle theta, oh my goodness, what is that? All right. I don't know how to make it stop doing that. Okay, so this angle theta here is going to be 30 degrees, right? So I draw out my right triangle so I don't mess up my components, and I'm going to use SOHCAHTOA. And then the last part of this problem is obviously there has to be some friction, right? The reason we know there's friction is, well, look, there's a mu sub k. So this is a combination. This problem here, it's dealing with friction, right? But there's a force that's being applied at an angle. And then more importantly, also, there's a little bit of kinematics, right? So your kinematic relations, they are going to be on the equation sheet. I can also write them up on the board. But, this is something that was coming up during the review problems. We had to bust out the kinematic relations. So we'll go over them now. First, let's just get through this problem, and we'll see which one to use. So we have 200 newtons of applied force. I did not mention what the weight is. So the weight, we're just saying the weight is 120. Okay, so the weight's given. It's 120 newtons, right? So it has a mass just over 12 kilos, but they just tell you what the weight is straight up. And we need to solve for t. How long is it going to take to push this box 2 meters? So let's, I'm going to draw the free body diagram a little again, just to make it a little bit more clean with the actual numerical values. So I know I have 120 newtons going down. I have some force that's at an angle. Whoa, what? Okay. So I have some force that's at an angle. This is 200 newtons. All right, and I got my components here. And then I have a normal force going up. I don't know what that normal force is. I have to calculate it. Okay. And then I have some friction force that also I'm going to have to calculate. All right, and then we'll solve this problem. So here, this x component, or this component that's horizontal, let me use a different color here. So this component here, we see that is the adjacent side to the angle. So I have a 30-degree angle, and it's adjacent to that angle. So I'm going to use cosine. So that part right here, that's 200 times the cosine of 30. And this part over here, that vertical component, is going to be 200 times the sine of 30. But something that's important to note, it's going down, right? So that vertical component of this applied force is actually going in the negative y direction. It's going down in the same direction as the weight of this box. So what that's going to do, effectively, that's going to make the normal force larger, right? So this is why this is an important example, because there's so many of where you have something on a flat surface and a normal force equals the force of gravity, right? That's kind of gone into everyone's head. Clearly on the inclined plane, normal force is not equal to force of gravity, right? We see that in most cases, normal force is equal to mg cosine theta. It's equal to a component of gravity. In this case, the normal force is equal to gravity plus this component of the applied force. So let's just write out our forces. use Newton's second law, right? So we know the system's going to accelerate. All right, F net equals ma. And let's just analyze our forces in the x and y direction. So here, the box is resting on the ground. It's not an elevator. It's not accelerating up or down. In the y direction, the forces are balanced. So in the y direction, right, the force is balanced. But in the x direction, it's not. It's going to accelerate. There's going to be a net force. We have to actually calculate to make sure, but let's go through it. So in the x direction, I'm saying there's a net force. And I need to set it up based on the forces that are being applied, or at least the forces that are found in the free body diagram. So I have this 200 times cosine 30. That's my applied force, right, times the cosine of 30. And that's going to the right. And then my friction force is going to the left. I don't know what it is yet. I have to calculate it. All right, but I'm just writing out the expression. All right, so this is my expression for the forces in the x direction. In the y direction, I know that the net force is 0 in the y direction, that is. So that, so they have to balance, right? So the forces that are going up in the positive y direction, normal force is holding up the box. So I got force normal. That has to equal the weight force that's pulling down. That's 120 newtons. And there's this component of the applied force that's also going down, right? So I have usually, right, if there's no forces at an angle, normal force is almost always equal to the weight. In this case, because I'm pushing down on the box, right, I'm pushing down and to the right on the box, I'm increasing the normal force between the box and the floor, right? That's the basic idea. And that is 200 times the sine of 30. And right off the bat, I know this is basically just 100, right? So sine 30 is 1/2, 200 sine 30. That just comes out to 100. So my normal force is actually equal to, 220 newtons. Okay? And I can use this to figure out the friction force, because I know that the force of friction is equal to mu times the normal force. All right? So I'm just going to plug in the values. I have 0.50 for mu. I could put mu sub k. It's sliding, so it's kinetic friction, times the normal force of 220. And I end up with 110. So that's my friction force. I'm plugging this back into the original equation. So I have ma. I know there's a net force in the x direction. I have this applied force, so 200 times cosine 30. All right, so I'm doing this one step at a time, just so it's not confusing. So I have 200 newtons of applied force, but the component of that, so this is the horizontal component. So cosine 30 minus 110, right? So the friction is going against the motion of the object, right? So the applied force times cosine 30, that's pushing it to the right, and friction is going to be going to the left. So now I just have to do the math. Here I have 200 times cosine 30. I got 173.2. So basically it's 173.2 approximately minus the 110. And I end up with minus 110. 63.2. So 63.2 newtons. That is the net force in the x direction, right? So that's equal to ma. And I know that the mass, so this is actually tricky because we tell you the weight. So the weight's given, not the mass. You have to actually figure out what the mass is. So I know that the mass, the way you're going to do this, I know that the weight, so I just want to write it out completely. So the weight is the force of gravity, right? So those two ideas are interchangeable. That's what weight fundamentally is, the force of the earth pulling us down. And we know that's equal to mass times the gravitational acceleration, right, mg. And on planet Earth, that's 9.8. Right, so g equals 9.8 on Earth. Okay, so if I have the weight in newtons and I need to find the mass of the object, the mass is equal to the force of gravity, which is the weight, divided by g, right, the 9.8. So I got 120 newtons divided by 9.8 meters per second squared. Do that in the calculator. So 120 divided by 9.8. I get 12.24, let's say 25. So 12.25 kilograms. Okay. And that's pretty much it. So now, I don't know why the iPad does that. All right, stop. So here, I need to solve for the acceleration. So I take my net force in the x direction, 63 newtons. I'm going to divide that by the mass, the 12.25 kilograms, and that gives me the acceleration. So, all right, I need to figure out this setting. I don't know why I keep doing that, but stop. All right, hold on 1 second. Stop. Okay, there we go. All right, so 63 divided by 12.25, 5.14. So I get an acceleration of 5.14 meters per second squared. Okay. And now what were we trying to do? Oh, how long does it take to accelerate 2 meters? All right, so this is our acceleration. Our x is 2 meters, right? So it's something else that's given. Our t is unknown. And let's just assume this starts at rest. So it starts at rest. All right, so again, I just made up this problem, but because I couldn't find one that's similar enough in the homework. But this is going to be a very useful problem. I'm going over it for a reason, all right? So I want to make sure we know how to do it. So it starts at rest, right? Our initial velocity is 0. Okay, so V naught is 0. So the kinematic relation that has x, t, V naught, and a is the third one, right? So the equation of motion, I have V naught t plus 1/2 at squared. I know that my V naught is 0, so it kind of simplifies the expression. I have 1/2 at squared. I need to solve for t, so I'm just going to do it one step at a time. Multiply both sides by 2, then divide both sides by a, and then I take the square root of both sides. So square root of 2x over a, and we are almost done. So 2 times 2 meters divided by an acceleration of about 5.14 meters per second squared. And let's see what we got. So 2 times 2 is 4. Divide that by 5.14. I got 0.778, and then I'm going to take the square root of that. So I got 0.882. Let's see. All right, let's say, all right, so 0.882 meters per second squared. If you have, let's say it's 2 sig figs. All right, so 0.88 meters. Oh, whoops. What am I saying? This is a time measurement. Be careful with your units. So used to writing meters per second squared. We're solving for time. Time's going to be measured in seconds. So if I have meters over meters per second squared, that ends up with a dimension second squared, square root of that, seconds. It's 0.882 seconds. And that's my final answer. And there we go. So this is a useful problem. We have a force at an angle, using friction, solving for normal force, and then using a little bit of kinematics, right? So that's an example that there wasn't a direct one in the review, but I wanted to make sure we covered it. So recap, we talked about vectors. We did some tension problems from the class kick. One more about tension, I just realized. So the one from the class kick's a little bit different, but it should be okay. So for this one in particular, because this is originally the example I was going to do, this one, you have an angle with respect to the horizontal. All right. So you should be able to figure this one out. I believe that the one in the class kick is not exactly like this one, but I'm not trying to give everything away. You're using the same process, Newton's second law. You're you know that it's an equilibrium. The forces have to balance, and you have to solve for the unknown for that example. This one here was an example that wasn't like in the class kick. We did I would say probably one of the harder problems on inclined plane from the class kick. That's what took up most of the time. And it's just basically going through the analysis, right? So we saw, 3 different versions. It's accelerating. It's a constant velocity going up the plane, constant velocity going down the plane. And this is going to be a very, very useful example. If you understand this one perfectly, then you should be good. If not, if you want a little bit more practice, we have a full review day before the test. You should ask questions then to really make sure you got inclined plane nailed down. But yeah, that is pretty much it. I mean, that's really, really all there is to it. I don't want this video to drag on for too long. So if you have any questions, just let me know. And hopefully we do very well on the test.